With this short all and everything and Hi, good morning. Welcome to the last day of this workshop. I just have one quick announcement. At noon, or whenever we finish the last lecture, there's a picnic right outside the Hurley Hall, a communal meal.
One can tell it's the last day. Huh?
Yes, yeah. There's chocolate.
Oh, really? Oh, good.
Can you turn this on, please? Yeah, good. Yeah, it's turned on.
Okay.
Okay, so.
Okay, so today I promised to talk about Eigenvariants. So we'll see how it goes, but I'll try to maybe briefly mention a general conjecture, but I'll try to function today by examples. Okay, so that will be like a little bit different than a compensation for the previous talks, which were pretty theoretic. So let me start by the familiar example in this lecture that we already saw, which is the Cogot-Leopold p-adic function. So the idea is that, well, so people first studied p-adic functions to understand the arithmetic properties of special values of classical functions. But once you start having those objects, you can ask whether there are like some genuine new properties arising. Okay, so let me recall. So we saw in lecture maybe we saw the Cogot-Leopold. So there will be basically three parts. So like the Cogot-Leopold, and then the Maser-Teitelbaum p-adic function for elliptic curve. And then, if time permits, I'll talk a little bit about Katz's p-adic function. So it'll be like basically three parts today. Okay. And yeah, then we'll be like to make in your head some picture that fits the three together. So the Cogot-Leopold p-adic. Well, so the data, the automorphic data, if you want, is the way all this workshop started. So we have this Keke character, sorry, this Dirichlet character, for finite order Keke characters, they're called Dirichlet characters. So we have this character which is supposed to be odd, so that's important. So odd means that chi of -1 is -1. And attached to this character, so Cogot-Leopold attached a p-adic function, which is a distribution on ZP cross, but today we'll talk about derivatives. So we'll take the Mellin transform directly. So there exists a analytic function. So LP chi is shift by omega p s. So there's a type-Euler character, analytic in S. You can think it analytic like in ZP, or if you want in CP, I mean, once it's analytic, you can feed in any p-adic number. Okay. Such that for any k, at least one integer, such that it's in the same disk, so p-1 divides k-1. We have this LP of chi omega p of 1 minus k equals to 1 minus chi of p e to the k-1 L chi 0. Okay, so it's very tempting and actually allowed here plug k equals 1, right? So if you put k equals 1, so assume. So first there is a fact, which is from analytic number theory, which is that L chi 0 is non-zero. So that's because well, I mean, you know by Dirichlet's theorem that L chi 1 is non-zero. And if you use the functional equation here, and the fact that chi is odd, you can okay, so Dirichlet, like this is also how Raghuram started. So this is non-zero. So this is Dirichlet. And actually, here, because chi is odd, this implies that like the functional equation. So you should appreciate the fact that we are working at a point where it only exists by analytic continuation. This is somehow the sum of it's outside the range of absolute convergence, and so it's easy to see that this is non-zero. So this thing here cannot vanish. So therefore, if that thing is to vanish at some classical point, so at some integer, of course it can have some p-adic zeros, that's a different story. But so it follows that so this is a trivial zero phenomenon. The same, it's like the Riemann zeta function has those zeros at the integers, so p-adic trivial zero phenomenon. Is that if k is 1, so if you want this to vanish, you need this to be a 1. This is a root of unity, so your only chance to succeed is to take k 1 and to have chi of p to be 1 as well. So if k is 1, and if in addition, so chi of p is 1 as well. So for example, if p is converted to 1 mod n, for example, then the p-adic function vanishes as well. Nevertheless, it vanishes. Okay, so let's call it trivial zero. And of course, what I mean trivial zero, I mean that there is an obvious implication, which is that if the L function vanishes, by this property, the p-adic function will vanish as well. And usually that's how the interpolation goes. I mean, the p-adic function is some factor p times a classical function. So some people call this extra zero phenomenon, because we are getting, in addition to the classical zeros, we're getting some extra zeros. Okay. So there are two questions to ask, which is when something vanishes, what is its derivative? Okay, so that's like a first question. And the second question is what is the arithmetic reason behind this vanishing? Okay, and those can be both quite easily answered here. So the first okay, so there is the Ferrero-Greenberg-Ross theorem. Ferrero and Gross prove the formula. Well, they show that if you do the derivative of this thing at 0, well, so they show that first that's non-zero, and you can divide it. There is no reason for that to appear, but anyway, if you have two non-zero numbers, you can divide them. And they show that the derivative is not the L function, but it's the L function times something that they call L invariant. it's a purely p-adic notion. There is no L invariance over C. And they give a formula for this invariant, and I'll try to fit in the board that remains both somehow the theoretic explanation and the formula for this L invariant. I mean, they proved the formula like that I'll give now. So the theoretic explanation is that this thing is a baby case of the block-Kato conjectures. Which I'll illustrate in the second part of the talk in a more meaningful way. I'll just here write some cohomologies, and when I go to the second part of the elliptic curve, maybe it will make more sense. So what's happening? What's happening is that maybe I go to the okay. Oh.
It's right.
Oh yeah, it's right. Okay. Let me just say so what the block-Kato conjecture is when you take like V, this motive, or for me motive means like a p-adic Galois representation, p-adic like in John Stokes, p-adic representation of like Galois Q bar over Q. So there is this block-Kato conjecture which says that the order vanishing at s equals 0 of the L function of f and s is supposed to be the rank or the dimension, if you want, of the H1 Q. You used to Galois cohomology. Shall I put Gal Q or just Q is okay? You've seen Galois cohomologies in your see some moving. This, and then you put like V, like the motivic dual, V dual, K twist by 1. Okay, and here there is this F. So this F, I'll explain. So means everywhere unramified. And I put like quotes because unramified P doesn't really mean unramified, means like some subtle conditions. So I mean, of course, if you want something to control vanishing of an L function, it better be subtle. So the subtlety here is kind of with P. I mean, right. And let me stay on the right side here and explain like what are these groups. So for so here we're in this case V is just V is just a one-dimensional vector space, so V is just QP or QP bar if you want, chi. So the Galois representation is just a chi starts from Galois Q bar over Q, quotients through like Galois projects to Galois H over Q. And injects in Q bar, which I can see if I want to write a complex L function, or I can see QP bar if I want to see a p-adic L function. And so H is the fixed field of chi, right? I mean, so H is some Galois cyclic extension of Q, which is the fixed field of the kernel of chi, right? Okay. So so fact, I mean, there's like so there's like what's called Kummer theory. So Kummer theory it allows one to compute this H1F of H QP bar of 1. that's just constant representation twisted by 1. So by Kummer theory, well, so by Kummer theory, the H1, these are just units. And because of this F condition, I mean, they should be like global units. So these are kind of S units, where S is the empty set. So these are just, so this is probably the only case where it's really easy to explain what's a Bloch-Kato Selmer group. So I mean, if you know the class number formula, it gives you the order of vanishing of a L function of a character at 0 in terms of number of complex and real embeddings. And if you know Dirichlet's number theory, here the Dirichlet's class number 4, I mean, Dirichlet's unit theorem to start with. If you know Dirichlet's unit theorem, you know that the rank of the units is related to the complex and real embedding. So if you put these two together, you interpret the order of vanishing of a L function in terms of rank of these units, and the Bloch-Kato-Selmer groups are supposed to generalize to abstractly those units, right? So that's Kummer theory. There is an exercise that this is exercise on Dirichlet's unit theorem. Is that because chi is odd, the chi part, which by definition is, I don't know if you're used to this kind of formalism. You take a abelian group, you tensor over C with QP bar or any algebraically closed group, and this allows you to take a chi part. So a chi unit is not really a unit. You can think of it as a product of units to some algebraic powers, or it's what's easier to think of is a log of a chi unit. It's a linear combination, a honest linear combination of logs of units, but the coefficients are in Q bar. Okay, so it's not really a unit, it's like exponential of a linear combination with Q bar coefficients of logs of units. Okay, because it doesn't really make sense to raise the unit to a power square root of 2 kind, right? It makes sense once you know what's a p-adic log, but anyway, but just abstractly, that's some module. So this is if you know this group G, I mean, obviously the units is some kind of a G module. So you tensor with QP bar, it becomes G representation, and you can take the chi part, so this totally makes sense. And the exercise is that because chi is odd, this is 0. So that's an easy exercise, is that only the even characters appear in the Dirichlet's formula. And this explains actually the fact that this order is 0. So this is compatible. So this is compatible with Bloch-Kato. So this is as predicted. As predicted, the order at S equals 0 of L chi 0 is 0, which is the rank of this Bloch-Kato-Selmer group. Now, what's happening when we go p-adic? So when we go p-adic, so the p-adic version, sorry, getting small here, but it's the central board. P-adically, well, so p-adically, we replace L chi 0 if you want. You replace it by LP chi 0. Okay, don't worry about this omega p. Okay. And you replace the units, the chi part of the units, you replace it by the chi part in the p unit. So you took OH 1 over p units, chi part. Well, again, exercise in Dirichlet's unit theorem. I mean, there's the same theorem for S units, right? For any finite set S, because P is totally split. This P here splits totally here between here and H. It's P0 both, right? In this condition here, really means that, so this thing here, because chi of p is 1, it's really because of that, otherwise it would be 0. But because chi of p is 1, this thing is really like the regular representation of chi, because if you think about it, there's no unit. So what's this module? This module is just a free group over, I think it's a vector space, over the places in H dividing P. So that's right. There is no unit, so all P units are determined by their valuations. So this stands somehow the regular representation. This is like, formally speaking, like the induction from the decomposition subgroup to the whole value group of the serial representations. So this thing, if you take chi part, it will be a line, or any chi character is. So and that's our dimension. So here we find one dimensional. So we produced like something in the p units which was not in the units, and this is reflected in the fact that the p-adic function is getting an order of vanishing. Okay, so this is somehow the easiest way to illustrate the Bohr conjecture. Okay. I want to say right away that this, outside Kummer theory, so Kummer theory basically computes the Bohr groups of cyclotomic twists of finite characters. But as soon as you move just beyond that, it becomes impossible. So warning. If you replace chi p-adic by chi infinite order Henke character, so by chi a genuine Henke character Q, you should go to imaginary quadratic field to have Henke characters which are not Dirichlet characters of infinity type. Take the easiest one, like 1, 0, something which is not 0, 0. So such guys, I can put the word algebraic here, like in Raghuram-Stokes. I guess algebraic is effective to this. Such guys correspond, if they take rational values, they correspond to what's called the CM elliptic curve. And then this H1F, then the dimension of the H1F cubed square root minus b chi, it's completely unclear where it is. Often it's 0 or 1, but there are examples where it's like sporadically it can get very large. And actually, this will be my transition to the second part of the lecture. Actually, this is supposed to be, like formally, that's formal. So that thing here, it's formally the H1F. I put Q, I put the induction of chi, so induce from Q square root of minus d to Q chi. So this is an automorphic induction. If you take a Henke character of imaginary quadratic field, if you induce it theoretically, you get a two-dimensional Gauss representation, or if you reduce it automorphically, you get automorphic form on GO2. So this is really this is really in S2. I can actually give you a very precise thing. It's in S2, gamma 0, ND ring. N is take character conductor Gaussian, and N is like the norm from Q square root of minus B to Q of Gaussian. Okay, so that's really a way to model a form. And I'm sorry. Oh, no, it's okay. I don't have to twist that one. Right? It's okay. And this thing, I mean, this thing is supposed to be related to the order of vanishing at S equals 1 now, because I didn't put the 1 here, so it goes on the other side of this form F. So, well, that's a kind of non-trivial quantity, the order of vanishing of a way to form at the central point. It's as simple as, supposed to be as simple as the dimension of a Bocato-Selmer group for a Keck character. So they just illustrate how well it goes as soon as you move out of Kummer, away from Kummer's theorem. And that, so that's my transition. So let me, because like some people ask rightfully why we care about theoretical functions. So let me recall the Birch-Swift-Dark conjecture and the way people try to approach it using theoretical functions. So I'll probably really start to not to go too much to the left or to the right. Okay, so can you the curves if you want? Oh, sorry. I forgot just sorry. I forgot just to define the L invariant. Sorry. So the theorem of maybe I should keep this forward now. The theorem of Ferrero, Greenberg, and Ross, right? Is that, I mean, this formula there? So it's a theorem about the L invariant, because I mean you can always write the derivative being something times a non-zero number, right? So the only content is like, what's that number? So the theorem is that you take here this line here, you take a basis. This is QP bar times U chi. Okay, so U chi is this chi P unit. Okay, and the theorem is that it's quite amazing. It's like the L invariant of the L invariant of chi is minus p-adic log of U chi dividing by the order of P, which it's a P unit, right? So like P the denominator is non-zero. And that's unique because if you replace U chi by, okay, so it's multiplicative. So the line, take another element of the line is like squaring, like bringing U chi to some power. It's a multiplicative line. I mean, if you replace U chi like by U chi squared, this is multiplied, like the order becomes twice and the log becomes twice. So that's really well defined. Okay, so it's a transcendental number. Actually, it's a theorem that this thing, this is a famous theorem of Baker and Broomer, that this thing is not in Q bar. So it's a symbolic number, but it's not an algebraic number. Okay, so that's the thing. This is it's such a famous theorem. So this thing here is the Baker Broomer theorem. It's one of the most impressive theorems in transcendental number theory, and so in particular, usually that's the only way to. I mean, we don't care so much that it's not in Q bar. I mean, I don't know like the application of it, but I know an application of the fact that it's non-zero. And often these numbers, the only way to show they're non-zero is to show that they're not in Q bar. So, yeah. So it's a big. I mean, obviously, it's very interesting to know whether the invariant is zero or not, because that's related to the order of vanishing of the p-adic function, right? If it's zero, then it means there is like another zero in addition to the extra zero, so it'll be like a yeah. Okay, so
Sorry, so is that thing not in Q bar or is the U chi not in Q bar? I thought it was the U chi.
no, the log of u chi. I mean, what you can, okay, let me actually correct it. I mean, like, okay, okay, I have like plenty of space here. So I mean, so you know the notion of a Minkowski unit. A Minkowski unit is just a unit, such that, I mean, take a Galois extension to make things simpler. This one is Galois, right? So a Minkowski unit is just a unit, such that the G orbit linearly spans the units. Okay, it's like if you want to take a random unit, probably it's a Minkowski unit. Okay, so take a Minkowski unit. So this means that the units, like the linear space of units, I can put QP or QR, doesn't matter. Okay, it is just spanned by these units, so it's like the direct sum of QP bar G of U0 G naught 1 G the Galois G in G naught 1. I mean, when I say naught 1, I mean you can miss any of those. So like the product, I mean the sum of the product of all the conjugates, that's 1 by the unit. Okay. Okay, so when I say direct sum, probably you like it better, it's a direct product, I don't know. That's really the linearization. I don't know how you prefer this. Do you prefer it? I hope you don't get confused between the products and the sums. I mean, okay. But anyway, so what already here is exactly correct. So what is log of I can write it here. Log of u chi just means you take the sum for G in G of chi inverse of G times log, p-adic log of G of U0. So that's like exactly correct. Like you take your Minkowski unit, you move it by an element of the Galois, you take logs and you do a linear combination with a chi. So that's in the chi part. Okay. So that's exactly correct. And Baker-Brewer's theorem says that the logs, so these numbers are in Q bar, right? The units. So Baker-Brewer theorem says that the logs of algebraic numbers are, if they're linearly dependent over Z, they are linearly dependent over Q bar. So you see, this is in Q bar, this is in Q bar, but the whole thing is not in Q bar. That's the way transcendence theorems work. Like a log of transcendental number can very well be algebraic. But what's hard is like take a number which is algebraic, whose exponential is against algebraic. That's hard. So that's kind of theorems they show in transcendental number theory. It's very useful here. I don't know any other way to show such a thing is non-zero because it's like just, I mean, by the way, Baker is like, if you remove the p here, it's also true for usual logs. And Brewer is put p, so it's the same proof because it's relies on properties of log. Okay. So okay, so what's an elliptic curve? I mean, since some of you are starting grad school, pretty much everybody can see an elliptic curve, but it's just a line to define it. So so you want the solution of that equation, no double roots, and A and B and Q. So I want the elliptic curve over Q. So E is this plus an infinity point. And there is the famous p-adic conjecture. I was criticizing Nadir that he's using LLC, but I hope everybody knows what's p-adic. So it's that the rank of so by Monovel's theorem. This is an abelian group of finite rank, and the rank. So you ignore the torsion, the rank over C if you want. Of this thing is conjecturally the order of vanishing at S equals 1 of the L function of E, and people were making the joke that when this theorem was when this projection was made, it wasn't even clear that it has an analytic continuation to C, because this only converges, absolutely converges for real part of S bigger than 3/2. And I mean, maybe you can push it to 1, but yeah. But now this is a theorem of Wiles and followers that there exists a way to modular form. So every elliptic curve is modular. So this L function, modular means exactly that the L function is a L function of a way to modular form. So this is in S2 gamma naught of n, and n being the conductor of the elliptic curve prime. And that's all the result goes all the way back to Henke, that the L function well, the initial relative of Henke is like this for CM modular form. It's known this to have analytic continuation to C in a functional equation. So one can, the order at 1 is well defined. And yeah, so as a remark is that if E is CM, so for example, if I don't say something wrong, CM, for example, there is this elliptic curve from Koblitz book from the congruent number problem, which is to find, like rectangle triangles whose sides and air are all integer, like this elliptic curve. Check this curve. So this elliptic curve, it's a CM elliptic curve, so corresponds to a chi-d like there. Okay, so this corresponds like to a Henke character weight 1, 0. So, and even in this case, so these are particular class elliptic curves having complex multiplication. This makes life much easier for many problems, but not for BSD so far. Like even for this much more restricted class of elliptic curves, like the versus their conjecture is not known. And so one of the things you might want to do is, this rank, let's say over Q, like the dimension over Q of P of Q tensor Q over Z. Well, you can also compute it over QP if you want. This is also the dimension over QP of P of Q, QP, right? The same numbers, right? Rank of a lattice, you can compute it over any vector space. So, so this thing here, so this points, these are like units. So there's some abelian group. This is a solution to this equation, the same way units are a solution of some other equations. Okay, and you might want to have a homological interpretation of this group, the same way we had homological interpretation via Kummer's theorem for units, to make things more amenable and to be able to work more, somehow linearize the problem. In the cohomologies, they seem like difficult objects when you're a grad student, but as soon as you get the formalism, they're easy to manipulate, even if you don't understand the definition. They're like some some tricks that you can always make. And so this is what like Bloch and Kato did. So Bloch and Kato defined also defined this Bloch-Kato-Selma group. So they defined this H1F, which in this case, so in this case, what you do, you consider H1F Q, and I have to put some Galois representation here, and that's easy for elliptic curve, because for elliptic curve, just take the torsion points and Galois acts on those. So the what you do is it's a little bit like the units, but not exactly. So you consider that you fix a P. I mean, P is fixed now. You consider the P to the n torsion point. So that's over Q bar. I mean, they have some algebraic coefficients, but it's a projective system. I mean, if you take P to the 10 torsion point, I mean, if you take P times this point, this is P to the 9 torsion point, etc. So it's a projective system. You take the inverse image. So this is this has GQ action. And also because of the nature of profinite limits, it's a ZP module, right? I mean, it's a ZP module. That's just by the limit procedure. So you can extend. I mean, you can invert P if you want. You can go all the way to QQ regardless. Okay, and so Bloch and Kato conjecture that, I mean, actually it's more important. So this thing is supposed to be equal to this P of Q. I mean, this is modulo the fact that the Shafarevich group is finite. So first of all, like this stage Shafarevich group is a very difficult thing. So if we can get it out of the way, it's a good thing. I mean, somehow we have replaced this complicated group of points with something which, so that's like some quite simple two-dimensional Galois representation. All this is like what called like DF, F like for not F for finite, but F for the form. F. So this is the Galois representation John mentioned for wave 2 modular form. And okay, so I mean, this is some kind of a difficult condition at P. So these are local conditions. So what I want to say is that by definition, the H1F, what is the H1F? The H1F is the kernel, the H1F of Q if you want. This is the Bloch-Kato definition, is the kernel. You start from H1 without conditions, and you go to the direct sum for all L places of H1, you restrict QL. If you have a cohomology class, you can restrict it to local decomposition groups. And you want each time you restrict, you want to fall in H1F of QL. And for L not P, those are simple to define. But this is exactly like unit. So what's a unit? A unit is a unit in OH, is a unit in H, which is locally united V for each place V, right? I mean, like what's a plus or minus 1 is a rational number, which for every P, there's no P in the numerator, nor in the denominator. So there's the spirit here. Like you want you have replaced points, which is something complicated, by cohomology classes, which don't have kind of denominators at P or L for any L. Okay. Okay, so okay, so yeah, so apparently I won't really probably talk about cats, but I'll finish this quietly. So so there is another big name in this theory, it's Iwasawa. So And well, I define myself the Iwasawa theorist, and that's a sub-branch of number theory, which I'm most interested in. So Iwasawa, he was studying. It was started more classical. It was about class numbers of number fields, like class groups of number fields, and he had this idea to work in a tower. So instead of just considering a Q, you consider what's called this Q infinity, which is Q to which you are drawing all p powers of all pn, all p roots of units. Sorry. Say pn. Okay. So once we read cohomology, okay, so we have this H1F for Q, and this multi for this elliptic curve B. Here B is like B. And that's supposed to know something about the L function of B. So what you can do is you can consider the H1F. You restrict, I mean, it's like that's a subgroup, right? I mean, the Galois group above here, right? I mean, the Galois group of Q bar over Q infinity is a subgroup of the Galois group of Q. And the quotient is this Galois group of Q infinity over Q, which is CP star. So somehow by inflation this restriction, if you want to define a class here, it's enough to define a class here, but right. Well, you have lost something because that's some kind of a well, that's precise, but you have also won something because each time you have like a short exact sequence, if you take a module here and you restrict it here, you get action by conjugation of the quotient. Okay, so this thing here, what you have won is that this thing here is a CP double bracket. I'll just put CP cross, and I invert because I'm looking theoretically module. Or okay, forget this. So it's a module over this. This is called the Iwasawa algebra lambda. Okay. And so what the Iwasawa main conjecture says is that if you take the characteristic ideal, so each time you have a lambda module, if you look at this lambda module distortion, so you can consider what's called the characteristic ideal. And so this characteristic ideal is just an ideal in lambda. And if you remember the first lecture, there was this triangle with like a distribution and a Mies transform and a Meilin transform. I already used the Meilin transform to write the theoretical function of P. But if I use the Mies transform, the theoretical function is just an element of in the power series in okay. This thing, sorry, they're like things I don't know, like if you have opened ever Washington's book, there is a very elementary theorem of Serre that this thing is product of index from like 1 to p minus 1 of CP double bracket P's. So Serre proved that it's Serre's theorem. It's an elementary theorem in theoretical analysis. Is that if you take CP and you take a pro P group like 1 plus PCP here, pro finite completion, this is isomorphic topologically, and as topological algebras, it's isomorphic to CP double bracket T. Okay. So this thing here, so the Iwasawa main conjecture is that thing here is supposed to be equal to the theoretical function of generated by the theoretical function of P. Okay. When I say this, I don't really mean this, I mean the Mies transform of this. Okay, so I need an element in one. Okay. Okay, so as I mentioned in one of the talks, maybe I was asked at the end of one of the talks, these p-adic functions first were this was introduced. So this was introduced by Mazur, Tate, and Teitelbaum. So the p-adic function of analytic curve S was introduced in the England-Jones paper by Mazur, Tate, and Teitelbaum. In their quest to generalize DSD to p-adic functions. And well, and they made the same remarkable discovery that Kubota and Leopold made, is that this p-adic function has kind of extra zeros. So there is this there is this theorem which is due to Greenberg and Stevens. And it was the entity conjecture is the following. Actually, I can so take E over Q an elliptic curve. Which has having split multiplicative reduction SP. So that's a purely geometric thing. You reduce the equation of P, and it should be like two lines. So it should be band reduction, two lines. So it's not an elliptic curve. It's two lines crossing defined rationally. That's important over FP, not over FP squared, and crossing transversely at the point. Okay, so that's one of the topics. And that's a very easy thing if you have any geometric background, but if you don't have any, there is a much more complicated definition, which is in the spirit of this workshop, which is that by Wiles' theorem, E is attached to a Fe, which is weight 2 cusp form primitive on gamma 0 n. And having anything which is not a good reduction means that P divides N, exactly P divides N. That's the okay, so maybe another way, because maybe I like the what we saw in the lecture, that it put like this, and P does not divide us, P divides exactly once the conductor. And I want the local component, so I want the phi P from Raghuram-Stowe, which is attached to this. So the P component of the Dutch automorphic form, I want it to be a Steinberg. Okay? The STP. This STP, remember, what is kind of like the sum of this automorphic induction from P2 to GL2 of QP of like absolute value to 1/2, absolute value to the -1/2, like in the exercise sheet. It was given as an exercise. Okay, so there is automorphically means that's like the coolest thing that's not a spherical representation. Okay. Okay. Then, well, they first assumed that it's not necessary that. Anyway, so in the first kind of things they were assuming, just to spice it up, that that's not necessary. What I'll say after. Assume that the L function of V81 is non-zero. Then, nevertheless, because of this local condition, that's exactly like this phi of P, which is 1, but it's chi of P, which is 1. Then the p-adic function vanishes, still vanishes because of this local interpolation factor that one is putting, and its derivative is equal to like some mysterious number, which is called the L invariant here. times the value, the original value divided. Okay, so here there is something particular for Kubota-Leopold. We don't need periods because the values at negative integer, they're Bernoulli numbers, so they're already in Q, but in Q of chi. But here, I mean, of course, if you want to compare something p-adic with something complex, they both better be in Q bar. Okay, you cannot compare p-adic and complex numbers, even if that's something which is important. I mean, Q p bar and C, they are isomorphic as fields abstractly, but so even of course, like you can put like Q bar in both, that's okay. But of course, not like as topological. There's a bit different topologies. But this doesn't justify to write equalities like this because of the randomness of this isomorphism. If you ever prove that some p-adic number is equal to a complex number, you better prove on the way that they're both in Q bar. Doesn't really make sense to prove things like this otherwise. And the L invariant actually here, there is a formula and there is an amazing theorem which is called the Saint-Étienne theorem. That's a city in France, which is pretty much in the middle of nowhere, where I think 4 mathematicians have this inventionist paper, all from Saint-Étienne, who prove this L invariant is non-zero, and that's pretty much the only case where like beyond the Baker-Brummer theorem, it's known that the L invariant is non-zero. So the L invariant is, I start to doubt now if I should put a sign minus here. Don't know, Andre, because I'm putting these minuses in my notes. I didn't find a minus. It should be? No. Okay, I don't know why. I have to reflect on this sometime when I have time. So it's the p-adic log of something modulo or of the same thing, and this QE is some kind of p-adic period. So what's happening is that if you consider if you consider like the CP points of the elliptic curve, because it's P, it has this split multiplicative reduction. There is what's called Tate uniformization. It's like CP star. So CP star is like C, think of C star. C star is like C mod Z. And elliptic curve is like C mod 2 copies of Z. So if I want from C mod Z to go to elliptic curve, I have to quotient, multiplicatively here by another Z, which is this one. So, okay. And well, so as a closing remark, I want to say that there are other such examples. It's like an active field of research. And what I want to say is that the proof of this theorem actually uses the eigenvariety. So the proof of this theorem, so this is a one-dimensional theorem if you want, or this is along the blue line like in Jones-Stokes. So this theorem starts with like some theoretical function if you want. And this is like Jones blue line, which is basically you twist, you go to L, P, E, maybe I could put F makes more sense. F, it's like F2, right? S, or K if you want, or K plus 1 if you want. And this formula is like F2, you twist by the norm at 1. So this is kind of the twist direction. So the cyclotomic direction changing the S variable, that's like the twist direction. So the theorem lives completely in the twist direction. You don't need to know what's weight or anything. It's just like you take some color positional motive and you go with the twist. But to prove this theorem, you have to allow yourself this second direction, which is you go to, here, you go to the p-adic function of fk. I know that was very bad to put k here. That put r. This is the blue direction. Put R here, please. K is really the weight at R plus 1. So the way the proof works is that they define this p-adic function in two variables, and they use some kind of Leibniz formula. They transfer the differentiation from the S variable to the K variable. It's very tricky, and it's a fundamental paper in p-adic function. This rigorous given school of the laser data configuration. Okay, so yes, that's a good place to stop. Thank you. Richard.
Say more about the philosophy. Where you replace a
I
classical.
don't hear.
Oh, can you say more about the philosophy that when you replace a classical L function by a p-adic L function, you remove the ramification condition P in this unit example?
Yeah, actually, what did I write before? Right. Yeah. So I wrote the F here. Yeah, I should have put like a question mark there. Like the whole game. Yeah, exactly. I mean, yeah, here maybe it was too bold to put this. I mean, I was putting this F just by analogy, but so the whole game you want to play when you go to p-adic functions is that it depends from which side you attack the problem. From the analytic side, you construct some distributions and you construct what you can construct. I mean, I guess I don't know. But once you have something like, for example, if E is a CM elliptic curve, that's like constructing a p-adic function for the chi from the. Oh, I didn't write this guy. Well, it wrote a little bit of it. Like chi like this, algebraic character like this. So Katz constructed p-adic functions now in two variables like this, so they exist. And then the whole game is to define some Selmer group, which has for which the Vassalian conjecture should hold, right? So for example, in this condition, in this case, you put like ramified in one of the places and not in the other. Yeah, I mean it's. I mean, to me, like these formulations, I mean, beyond like the GL1 case, they are pretty much not clear how they should go in full generality. For example, Raghuram was making this remark that much of the research was concentrated on CM fields. He was trying to do the conjectures like or the algebraicity of L functions for totally imaginary fields. And yeah, I mean, it's a very, I don't know what to say, like so the Bloch-Kato conjectures are very well established. It's clear what's the group and this, but they're difficult to prove. In the Vassava theory, it's more like one has to find like the appropriate conditions to make things work. Okay, so I mean that's the level of my understanding at least. Maybe you know more. For those who stay next week, you're giving a talk on Iwasawa theory.
I'm not going to talk about this part.
Yeah.
Okay. So my question was about something else, but I understood the answer to my question because of what you said. So okay. Answer my question not directly.
Yeah.
I'm sorry, I apologize ahead of time if you actually said this during the talk and I missed it. You mentioned the first Dyer conjecture, which is about the order of vanishing of this L function that right curve. And then you connected the L function to p-adic L functions throughout your lectures. Has anyone proven instances of the Burson-Swinnerton Dyer conjecture using the p-adic method, using the p-adic L function?
Yeah.
Could you explain that?
It's not like it's someone like the only person who I ever. I mean, they're of course like Rosagi and like Polyvagin, but like all the. Okay, so first of all, let's be honest. I mean, like, depends what you call the person there. I mean, So first of all, as far as I'm concerned, replacing a group of points by a Selma group and a L function by a p-adic L function, I'm happy with that version anyway. I mean, that's probably the correct way. But to answer your question, maybe I would suggest to look like the recent papers of Chris Skinner and collaborators who call what, I don't know why people call these converse theorems, like so you know, like I remember workshops when I was a grad student. It was always going like, if the analytic rank is at most one, then the Burson-Simons conjecture holds. And today the theorem is if one or two ranks, like for example, if the algebraic rank is at most one, that also works. And the methods are purely p-adic to do this. So that's maybe one of the big achievements of the p-adic theory. Like nowadays, if the algebraic rank, and the algebraic rank is even better. Like if maybe even better. Okay. If the Selma group has rank at most one, so a priori this rank one can come. Okay. So then just because it's like too much with the hands. Like for the students, basically you have like the points. It's very rough. Like you have like the points. And you have like this Selma group, which is like this H1 F, and then you have this Shafarevich thing, which is the defect. Okay, that's very rough. So nowadays the theorem is that if that thing has rank at most one, then the analytic rank is also at most one. It's the same, and Shafarevich is fine. So actually, it comes from a point. So you confirm this?
I think that's only look for function field, but I need to check.
No, I don't care about functional field. So it's
Maybe
alpha symptoms.
but I need to check whether they need to synthesize.
Yeah, I mean, okay, so this is Dixit. Okay. Yeah, it wasn't clear for me either, like when I was reading, but I had a communication with Asher Burungale, who's one of the Chris Skinner's collaborators, and he sent me an email with references and yeah. I mean, so the answer is like yes, and it's even more yes that I'm saying like many people try to approach it this way, like where people actively work. Like for example, there David Loeffler and collaborators, they try to prove Bertrand Dyer in rank 0 for abelian surfaces. And they try to do this using p-adic methods for the eigenvariety for GSP4. So I don't know, maybe there are like some completely different approaches, but the people I know, they really try to use p-adic L functions and eigenvarieties to attack block cutting.
Thank you.
We keep this tradition of postponing schedules.
Yeah, no, we'll start at 11:15. Yeah.